Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@eapen.info. My guest today is Dr. Mehdi Anwar, who is a professor of electrical and computer engineering at the University of Connecticut. As a Jefferson Science Fellow, he served as Special Advisor for Technology Transfer and Innovation in the Office of Intellectual Property Environment, Economic Bureau, U.S. Department of State. At present, Dr. Anwar is assisting U.S. Department of State and other U.S. government organizations and the United Nations Office for the Least Developed Countries, Landlocked Developing Countries, and Small Island Developing Countries to stand up the newly established United Nations Technology Bank. Welcome, Mehdi.
Thank you. Thank you, Gil, for the very generous introduction.
So, one area of your research interest is the memristor, which I know has gathered a lot of interest lately, especially because of its possible applications in neuromorphic computing as we get closer and closer to the failure of Moore's law in conventional computing, and the quantum computers are not here yet in a practical fashion. So I would love to have a deep dive on the memristor area. What exactly is the memristor?
So, memristor was actually something that was predicted by Professor Chua at UC Berkeley in the 70s. And then a group led by Stan Williams, they actually reported the first memristor using titanium dioxide. So, as the name suggests, it is a memory resistor. It's a simple two-terminal device that remembers. And later, if you talk to Dr. Chua, the memristor shows actually a hysteresis in the IV characteristic.
Yeah.
And as far as Dr. Chua is concerned, anything that has a pinch-top IV characteristic happens to be a memristor. So that's an overgeneralization, but maybe he's right.
Right. So this is so the basic components in an electric circuit, I guess, is resistor, capacitor, and inductor.
That's right.
And this is sort of the fourth fundamental component there, right?
Exactly. Because the first three, if you look at it, like a resistor, simply relates voltage and current. And what you call an inductor will actually do the same thing because there is voltage and flux.
Yeah.
And a capacitor is charge and voltage. So a fourth one, which actually connects a flux and charge, was actually missing. And from that symmetry argument, Lian Chua was able to predict the existence of a fourth circuit element, which is the memristor. So over here at UConn, we actually, if you look at memristors, there are actually two groups as an example.
Yeah.
One particular group actually simply makes an assumption that there is something called a memristor. and what can we do using it. So they're actually, I mean, if I quantify them, they are actually roughly more than 95% of the research that is getting reported, saying that if there were something called a memristor, these are the things we can do with it.
I see.
And then there's a very small fraction of research groups where they are actually working on fabricating individual or crossbar structures and actually trying to find out exactly how to implement all of those ideas that 95% is actually what you call reporting.
Okay. So I know that Hewlett Packard came out in 2008 with much fanfare and announced that they have a practical version of the memristor. Is
Yes.
that true? Okay.
Yes. And at the same time, if I am not mistaken, so I could be wrong, but if I remember right, the idea was that memristor based flash memory will be actually what you call capturing what you call the memory market. But if you look at what you call the market, the thing is that's not the case yet.
Right.
And what we have found out during our experimentation is that I mean, it's not that our devices are the best, but still, after a few runs, let's say in our case it could be in the range of 50 to 100,
mm-hmm.
the memristor locks itself in a permanently on state.
Mm-hmm.
So that could be reversed. So using the HP technology, it's not that it's going to lock about 100 users. Maybe it's going to lock about after 10,000 users and so on and so forth. But there is that particular trend or tendency for the memristor to lock itself.
I see. So more generally, the memristor is something that has a state-based resistance, right? So
yes,
it can flip back and forth, and if the voltage is within a constrained range, it can hold that state. Is that right?
Yes. So as an example, if you simply think of hysteresis, that if I start fresh, so as an example, to get the whole thing started, we have to apply a slightly larger voltage, which is the electroforming.
Yes.
And again, we can come back to this one later because there are some of the applications may require that we come up with memristors without any electroforming, because that's actually will serve us different purpose.
Right.
But let's say once we have activated the memristor and we start from 0 voltage and we drive it positive, then it actually follows a rather high resistance path.
Mm-hmm.
Then after a certain threshold voltage, it actually simply switches from the high resistance to a lower resistance state.
Yeah.
And then as we decrease the voltage, it still maintains the low resistance. And at a negative voltage, it again flips and the IV characteristic keeps on repeating itself.
Right.
But the consecutive IV traces are actually different. And this is where we believe that the physical conduction mechanism actually comes into play. And that actually eventually leads to a memristor getting locked in a permanently on state.
I see. So the chemistry of a memristor, I know that you are experimenting with different materials. Is titanium oxide still considered to be the material to attempt?
The thing is, again, titanium oxide was the first one that was reported. And I believe HP, after that, used tantalum oxide. But if we were to pick, then the best material system is going to be either hafnium oxide or zirconia-based oxides, because they will allow you to, they will provide you the fastest switching times.
I see.
And hafnia is something of interest to technologists because it is actually compatible with the existing CMOS process as well. Because hafnia is the high-K dielectric that people actually use as the gate material, as the gate dielectric.
Okay. So there's also chemistry here is really the oxygen getting depleted and getting refurbished. What exactly happens
I
when
mean,
it's
the thing is,
depleted? Yeah.
unlike simple electrical devices where we simply have what you call electrical conduction, that is, which is or one particular component of the transport equation, which is current density equals sigma times electric field,
Yeah.
or more, it could be current equals Q and V, which is electronic charge, carrier concentration multiplied by the velocity. But in a membrista, it is not only electrical, it is also chemical, and also chemical in nature, because the initial aspect happens to be a chemistry. Okay, so that is something in electrical we were not used to dealing with, but now we have to.
Right.
So the chemistry actually, the chemistry part actually also adds up to the delay seen in this particular devices, because once I apply an electrical voltage, it is not that response is going to be instantaneous, because the chemistry has to kick in first. Once the chemistry has kicked in, and as we will say, that once we apply a voltage, then a physical process that actually allows the formation of a filament that will connect the two electrodes. Once that is complete, then and only then actually we see a switching from the high to a low resistance state.
I see.
And that actually takes time. So once we apply a voltage, there is going to be a delay. And after the delay, there's going to be a switching. And that actually can be controlled, as an example, if we scale the device.
So the read write operations, I guess. So one of the challenges here is to get that read write delayed to lower and lower timing. Is that one of the?
Yes, that is going to be a challenge.
Yeah.
And here actually material selection becomes rather important.
Yeah.
Because depending upon the material, the thing is, as I've said, that as an example, hafnia or zirconia actually has a better what you call a switching performance as compared to titanium oxide or tantalum or zinc oxide, which we have been using.
Okay. And the switching of the state has hysteresis in it. So I guess there is a lifetime of a memristor, and if I understand this correctly, Mehdi, I think you said it at some point it's going to get locked up, that it's not going to be able to perform anymore.
Yes. So what happens is that, as an example, when we apply a positive voltage, we have to, and our intention is to go from high resistance to a lower resistance state.
Yeah.
Then initially the chemistry starts. Ion will actually start to stack on the top of each other. And that actually is the filament that is going to be established, and that will eventually connect the two electrodes.
Yeah.
Now, when we apply a negative voltage, then we actually are destroying that particular filament. But what happens is, instead of filament being totally what you call destroyed and restarting from zero, there are remnants that is left behind. So when the next positive cycle starts, the filament formation starts from the other end of the remnant filaments. So each and every cycle, the filament has to, in order for us to complete the filament, we simply have to add only a few more ions to actually connect that particular electrode bridge. So eventually, after a certain number of iterations, the filament doesn't get destroyed at all. It simply remains connected. And this is what we call that it actually gets what you call locked in the what you call low resistance state.
I see. Okay.
So, and I think this is where important aspect is, this is where computer science actually comes in, that in order for me to read and write, what should be an intermediate process maybe is going to be a refresh, so that we actually ensure that length of the filament is zero
Hmm.
at the start of each and every positive cycle.
I see. Yeah. So that is why, I mean, there is excitement regarding the neuromorphic computing from different perspectives. But the behavior here appears to mirror some aspects of the brain too, right? So if you go to the neuron levels, I think we have something like 80 billion neurons and maybe 10 to the power 15 synapses in the brain. If we are able to model the neurons and the synapses using memristors, um, and these can I'm just speculating here, maybe. So these can not only store data, but also could behave like a computing unit as well, right? So it's our ability to model the brain in a better position with this type of technology.
Um, See, the thing is, when it comes to neuromorphic computing, and as you pointed out at the start of this podcast, there are different aspects using quantum computing. So different what you call research groups are actually pushing their own ideas.
Yeah.
But when it comes to memristor, so first of all, how does the brain compute? I mean, that I don't think is clear to us yet.
Mm-hmm.
And when it comes to memristor, you're absolutely right. That is, it can store and it can actually perform a logic operation at the same time. So this is what people actually have been using called implication logic.
Mm.
Things say A implies B. But the problem is that during this particular operation, one of the piece of information is actually lost. So that may require that we actually save it. So it actually, what I'm saying is, it actually simply, I mean, is making it rather complicated. But the other challenges, these material implication logic, which have been also demonstrated by the same group led by Stan Williams, in one of their Nature papers. The push has always been that we have to somehow replicate the Boolean functions that and, or, not, and so on and so forth.
Mm-hmm.
So my understanding is that whenever it comes to memristor, that maybe trying to implement Boolean functions may not be the right idea. We have to look for something else, something totally different. So first of all, the challenge is we do not yet know how our brain computes. That is, each and every synapse. Are the synapses have different categories saying one is going to perform logic function, the other one is going to perform, as an example, is going to store memory, or is the processing done in the memory while the memory is actually retained somewhere else?
Right.
So that is actually not so clear. And the other aspect that we talk about is like individual memristor versus crossbar structures.
Right.
So whenever we are addressing a certain memristor, there are multiple paths that will lead to the particular memristor. So there are sneak paths. And question is, and therefore people actually have used what you call a memristor that actually has a transistors in it, or as an example, diode, just to ensure that I'm going to address only one particular memristor, not the others.
Right.
But my personal feeling is that is actually making it too complicated. And I don't think there are diodes or unidirectional, or maybe there are, I don't know, unidirectional pathways in our brain.
Right. Yeah, so this is really fascinating, Megdi. So the crossbar structures, and I think, the general technology trend here appears to be, at least from the surface, that we had deep neural networks, so we have been trying to sort of model the brain using software. Now we have some interesting new technologies, and the approach appears to be kind of take what we have learned from deep neural networks and make it more efficient. But what you are suggesting is there is still some fundamental questions. How the brain actually behaves, how it stores information, how it computes, and till we have more transparency into it, we may have a technology that would fit into it, but we don't really know the processes well to actually model it, it sounds to me.
You're right. I mean, what we're trying to do is actually based upon the way we have done things, especially computing and electronics. Electronics is actually something that is predetermined, that if I apply a certain voltage, I get a certain current no matter what.
Yeah.
So it is totally predictable. And way we are using memristor is actually a simple replacement of a transistor or something similar to that. And we expect that it's going to behave exactly the way we have seen electronics to behave. So my understanding is that that may not be the right usage or utilization of memristors, because it's a totally different ball game.
Yeah.
So maybe as an example, in our brain, the most important aspect is, like, if I multiply two big numbers as an example,
right,
I may not get the exact answer, but I can get something that is reasonably close.
Mm-hmm.
So my understanding is, in a memristor-based technology, I do not want the exact answer. I want something that is close.
Right.
So if I would like to do something like that, then maybe starting from the existing electronics or transistor-based logic function may not be the right starting point at all.
Mm-hmm.
So we have to look at memristors, and we have to come up with an application platform that actually suitable to memristors. Because otherwise, it is actually what you say is trying to fit a square peg in a round circular structure or something like that.
Yeah.
So
Square
we are
peg in a round hole or something like
yes.
this. Yeah.
So we are actually trying to force something
Right.
That may not be the right way of actually utilizing the power of memristors.
Yeah. So going back to the brain, then it seems like, from a software perspective, like you say, what the brain does is very different from what we actually see from status quo computing architecture.
Yes.
Right.
Yes.
So it does classifications, but it does classifications along with anomaly detection, and it doesn't require very large amounts of data to be trained in a supervised fashion. So all of that implies that the way that we are looking at computing today and learning in computing is very mechanistic, and possibly not the way the brain is doing things. There was some maybe, I don't know if this is true, there was some hypothesis, I think it seemed to have died down a little bit, that the brain actually works like a quantum computer. But then the physicists have said that it's so wet, you can't really hold the qubits in place for it to do that. What is the latest thinking of the brain's architecture? Do we have any additional information?
I have not seen any, to tell you the truth.
Yeah.
And again, I mean, the thing is, though, I mean, things are changing. Like in the past, we have silos of electrical engineers, mechanical, or what you call psychologists, and so on and so forth. But in order for us to understand a brain and its computing ability and how it computes, it is not only what you call doesn't reside only in electrical engineering. It is actually a multidisciplinary approach.
Right.
That we all have to work together in order to understand exactly how it works and how can we implement it in a real hardware to actually try to replicate only a small part of it.
Right, right.
So the other thing that you mentioned, like training a membrista, like a human brain is actually trained from the day of his birth.
Right, yeah.
Okay, so it is getting trained, it is collecting data. And the question is going to be, so as an example, what I would like to do is, like one aspect of the brain is a tremendous amount of redundancy.
Mm-hmm.
So as an example, if I would like to implement a certain, what you call, application using membrista, and instead of pinpointly selecting a particular membrista to get it done, I would not do it at all, but I will actually have a built-in redundancy of this in the system. And my understanding is that if I have what you call a redundancy beyond a certain threshold, all of this sneak path, what you call effects, will actually be insignificant in a system.
Right. Right.
That is, instead of having a 20 by 20 crossbar, if I try to implement it using a 200 by 200 crossbar, then the implication or then the impact of the other sneak paths will not even show up.
Right.
That's something I believe, and that actually makes it simpler to what you call implement a crossbar structure without the complicated electronics. That actually makes it even more complicated.
Yeah, that's really interesting. So, I don't know too much about it, but when we think about redundancy of the brain, it might be that the brain is running multiple experiments on the same problem and then picking the one that is dominant.
That's a possibility.
Yeah, yeah. So, when they do dreams analysis of dreams, one suggestion is that brain is practicing, and there are different scenarios being run simultaneously, so that it can pick the dominant choice. And because of the sheer size of it, in terms of neurons and synapses, there is a lot of redundant capacity there. So when presented with a problem, it can create its own hypotheses and test it all simultaneously, and come up with a reasonable answer, even if it hasn't been trained on similar labeled data, large amounts of similar labeled data in the past, right?
Yes, yes. I mean, that is always a likelihood, uh, uh, because it has the capacity, as you mentioned, to run multiple experiments at the same time. But one thing, my understanding is, and again, it comes back down to how does the brain compute?
Yeah.
Is it pattern matching, or because again, if you are walking, as an example, and you see a certain face,
Right.
then all of a sudden it reminds you of someone else, and you think, "Oh my God, that could be my friend," and I last saw him 30 years back.
Mm-hmm.
Because the brain automatically tries to age that image, and it looks at certain features that are unique.
Mm.
Okay, so, and my understanding, and that has happened to me because I saw a friend all of a sudden after 30 years, and I said, "Is that you?" And to tell you the truth, the face was different, but there was something that actually was a match, which I don't know exactly what.
Right, right.
Okay, and there's also a possibility you will actually say that and you'll be proven wrong. Okay, so the brain actually has a certain thing that it actually looks at certain things in a certain way.
Yeah.
And that actually points to the way it actually processes data.
Mm.
So it may not be that it is actually doing the ones and zeros and rounding them off. That's totally different.
Right, right. So it is thinking more analog fashion,
Yes,
right? Yeah.
that's what I think. And it is actually matching images and trying to find out exactly if there are some unique features that actually relates the two images. And if it does, then it actually flags it.
Right. And what you mentioned in terms of, so you see somebody you haven't seen for 30 years, but it's still able to create a proxy for the
Definitely.
data that it has stored in and age it for 30 years and still come up with, it's anomaly detection rather than
That's right.
classification, right?
That's right.
and
Exactly.
extremely
Exactly.
powerful. Yeah.
Exactly. And the thing is, this is something we actually have discussed in the past. Like, the application of memristors.
Yeah.
Like in our brain, sometimes our synapses cease to function or they get stuck.
Mm.
So if you remember, people actually remember what they did when they were young, but they forget recent events.
Right.
That is, the memristors are no longer functioning and they're actually getting shorted or connected to actually one of the previous pieces of information
Mm.
or the previous cycles. That means they can't refresh it anymore. That's what's happening. So in that particular sense, a memristor and a synapse, a synapse that is aging or getting impacted or affected by Alzheimer, and a memristor that is actually getting shorted actually behaves in a similar fashion.
Mm.
But that doesn't imply that trying to refresh the memristor and trying to refresh the synapse is actually the same thing. But
Right.
what I'm saying, there's a certain degree of parallelism in between the two.
Right.
Will one lead to the other? That is actually a very, we are stretching it a little bit, but that may not be the case. But it is funny to see when we actually see this particular aspect
Yeah.
in the two.
And so the shortening of the memristor, is that a function of use or something else?
No, it is actually, it's a memory resistor.
Yeah.
So it simply remembers because the charge is actually is getting accumulated, so it remembers exactly what happened in the past.
I see.
And it's a two-terminal device like a resistance.
Yeah. So now I was trying to draw an analogy back to the brain. So aging seems to reduce our capacity to learn. Clearly, reduce our capacity to learn new things.
Yes.
It in the absence of disease like Alzheimer's, we still seem to be able to retain information from long time ago,
Yes.
right?
Yes.
And so how do you define? So aging tells us that our capacity for computing is declining. Is that the way that
Yes.
you would think?
As the thing is, like as an example, again, as you mentioned, it is a read and write.
Yeah.
So if as a memristor, after a certain number of what I call cycling, if it gets locked in a permanently on state, it has ceased to learn.
Right.
And doesn't matter what we do to it, it's not going to remember because it doesn't because the filament is actually always is connected in between the two electrodes.
Yeah.
So it's going to remain something in the past, not the present.
Right. Right.
So in a similar fashion, a neuron, when it can't process anymore, it actually gets locked up into a state that is the past.
Right. And it loses the elasticity, so to speak. Right?
Exactly.
Yeah.
But again, it's a stretch because just to make this comparison, but it reminds, when you're looking at it, there is a great deal of parallelism in between the two.
Yeah, and memory at that point it relies less on elasticity because it doesn't have to learn anymore. It just has to essentially read it, and that's okay even in a locked stage, I would imagine, right?
Yes.
Yeah.
Yes, exactly. And at the same time, this is where the fun part is, that if I have Alzheimer and I remember things in the past, so I said, I forget and I say, it seems that I'm in the past. Or in other words, I'm actually not using my logic anymore.
Yeah.
So the understanding is that whenever I'm getting stuck in one of the old memory states, synapse is not functioning. Does it imply that the logic operation is also not functioning at the same time? So there is that something. So what I'm trying to say is, we need to somehow extract that particular information. That is, how does the brain compute? And it's not that a memristor is actually going to be a replacement for that particular kind of computation. It can be something totally different.
Right.
But it is something similar to what we are looking at right now.
Yeah, I wonder the power consumption gives us any clues. I mean, the brain appears to be so efficient
Yeah.
from a power consumption perspective. I
Yes.
don't know if that gives us any clues at all.
I mean, that is something also one of the part of the equation, because whenever it comes to electronics, it is actually a brute force that we apply.
Yeah.
Like if you remember, in the very old days, what you call the supercomputers are based on what we used to call emitter coupled logic,
Mhm.
and the only challenge was to simply try to cool them down because they were running so hot.
Yeah.
So on the other hand, yes, the brain consumes the maximum amount of energy, but still it's a very efficient system because it does not dissipate that much power.
Right.
So it is a very what you call it's a what would you call what do you call it's a heavily parallel system.
Yeah.
And it runs very slow.
Runs very slow.
And that's the way to get computing done. A great deal of redundancy with superbly parallel computation, but let it cycle or let it be clocked at a very low clock rate.
Mm. And is the fact that data and computing are co-located,
Yes,
so you don't have to shuttle data back and forth, right? So that
that's
also
right. That's right.
Yeah.
And I mean that actually has what you call implication.
Yeah.
Because and that actually leads to one of the questions that people have been discussing, which is the non-von Neumann, what you call computational platform, where we do not have to, in order for us to compute everything in a CPU, we don't have to what you call fetch data and then put it back again.
Right.
Because A, it is actually slows the process down, and B, during this particular process of what you call transferring data back and forth, someone who's going to be sniffing around will actually know if that person is smart enough that this is the computation we actually are working on. And that actually is a security threat as well.
Right. Right.
So in-memory computing actually will make things faster. At the same time, it is much more secure than the computational base that we have right now.
Right. Yeah. Yeah, that's an exciting direction. So your current research, maybe, so there should be some material sciences based innovation here, right? So read write timing, having a larger number of cycles before it becomes locked in. All those appears to be ultimately a material sciences problem.
Yes, the thing is now what's happening is if you look in the past, electrical engineering always was what you call dependent a lot on material science.
Right.
Like electronics, we started from silicon, then we went to gallium arsenide, then we went to gallium nitride, and all of these things, depending upon application, material science always had something ready for us that we actually can use. But now what's happening is it is so all of these devices initially, if I'm talking about modeling, I can simply do electrical engineering and I'll be all set. The only thing I need is mobility and conductivity, and that takes care of it.
Mm-hmm.
But when we actually went to, let's say as an example, gallium nitride, which is a material system for high power electronics, we found out that electrical is not enough. We also need to take into account mechanical engineering because stress is also a factor, because these are all piezoelectric material.
Right.
So before it was electrical and material science. Now it became electrical, mechanical, and material science. Now comes Memristor, where part of the process is actually chemistry driven.
Yeah.
So now we have widened it again. It's electrical, mechanical, material science, and chemistry or chemical engineering.
Mm-hmm.
Now you're talking about application. And by the way, computer science was always there, because whenever you talk about using these electronic devices in certain what you call application platforms such as computing.
Yeah.
Now you're talking about it is not only electrical, mechanical, material science, chemical, and computer science. It is also physiology and neurobiology that actually comes into the play.
Right. Yeah, especially thinking about the brain. So
Exactly. So it actually becomes, and the worst part is that it's actually have a common lingo so that we actually can discuss the same item and try and make and understand exactly what we are discussing. So far, we understand the lingo of computer science and material science and mechanical engineering, but physiology and neurobiology, that particular language, we are not that accustomed yet.
Right. Yeah. It's exciting times. Like you say, I think innovation is going to be at the intersection of many fields coming together. Right.
Yes, exactly.
And if we are successful there, it's really truly a step function change in terms of our understanding and capabilities.
Yes.
So I want to close with your thoughts on neuromorphic computing. So I know that we are running against some fundamental physics related constraints on conventional chip. There have been some advancement in quantum computing, but it seems to be still difficult to accomplish. And so what do you see next 5 years from your perspective, Memristor or other such component-based modeling of the brain? Where do you think we will be in 5 years from now?
I mean, again, I'm slightly partial towards Memristors.
Yes.
But and the only reason I think Memristor is has an advantage because it's a very simple device.
Yeah.
As compared to the other what you call application platforms such as the quantum computing and so on and so forth.
Yeah.
So it's a very simple two-terminal device that can be scaled, and the material is actually research is actually very mature, so that we actually can use it to implement things.
Right.
But the only challenge is, as an example, we are still talking about fan out as an example. In a memristor, my input is a voltage, but my output is resistor or current.
Yeah.
Resistance or current. So fan out doesn't compute that well in a memristor system. So what I'm saying is that we are still using the parameters that define traditional electronics in order to quantify memristor behavior.
Right.
And I don't think that is the right approach.
Yeah, so that opens up a really exciting area, right? So we could potentially throw out, if you will, sort of the conventional ideas around computing, and take emerging technologies like memristors to really go to areas that computing hasn't really attempted to do so far.
Exactly. And as you said, maybe analog computing is the right way of doing it, or something different.
Right. Yeah. Hopefully, it's an area that is progressing. Really appreciate you spending time with me, Megdi. And
no, Gil, thank you for giving me the opportunity. It was really fun.
Thanks so much.